Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture 18. As in lecture number 17 and 16 we have covered the unbalanced movement, some examples over it, and now this is in this lecture basically I am covering a new example, and it is a very extensive example. Okay, and here you will see a flat slab system, 30 by 30 feet panels and 20 by 20 inch columns supported slab. So in this lecture basically this is the panel system, and what topics we will cover in this lecture: how to design how to fix flats and drop panel sizes, okay, and one way and two way shear, how to check basically the requirements of a flat slab system in two way and one way shear. But we will discuss very thoroughly the unbalanced movement, the shear or the flexure shear caused by the unbalanced movement, which will be a further addition with the one-way and two-way shear. Okay, equivalent frame method we will be used to analyze this flat slab system, flexure and shear design of that flat slab system, how to calculate unbalanced movement in the case of the interior column, in the case of the exterior column, and in the case of the corner column. And this is the new topic which I have included in this lecture, that is how to design axial, uniaxial and biaxial column, how to basically determine the movements which is transferred from the slab to the column. So this part will be more interesting for you people. And checking the flat slab system by SAF, this is also further addition, that I will check the flat slab system, my calculation work SAF. Clear? Now the flat slab system consists of 30 by 30 feet panel, and we have four axes in the x direction and four axes in the y direction. The partition loading is given, that is 20 psf. The lie load is given, that is 60 psf. And remember, this slab system is basically designed for the vertical loading, not for the lateral loading. This is assumed here that the lateral loading will be taken by the shear walls. Okay, so this is a non-sway structure system, right? The use of the flat slab system will be checked. If the use of the flat system is not adequate, if flat system, right? Flat system is that slab system which have no drop panel column capital, right? So if it is not adequate, you have to then use flat slab system, right? And flat slab concrete floor system is similar to the flat system. The only exception is that the flat slab use drop panels, right? Now this is basically the calculation work which I will share. But one thing I clear you, that you have to go to my YouTube channel, and here you have to search basically this. You have to go to my YouTube channel and this playlist, right? Now here you see this playlist. In this playlist you will see from lecture number 1 to 17. You have to watch all those lectures from 1 to 17, because if you don't watch those lectures you couldn't understand this present lecture, because all the things I have already explained here. I am not going to explain those things again, right? Similarly, I have already uploaded a flat slab system, which is basically I have thoroughly covered here, right? The complete calculation work, how to fix the size of a flat slab system, how to fix the sizes of column capital, the drop panel, how to design that system, how to flexury design such a system. So these 15 lectures I have explained all these steps, right, very in very detail. Okay, so you have to watch those lectures before coming to this lecture, right? So how to fix the size of the flat slab system, ACI code 8.3.11, right? This is the section table, and here you will see this is the in 14. Okay, so these two formulas are used, right? There are different cases in flat slab system. When you have no beam, when you have interior beam, when you have edge beam, right? So in all cases you have to use different formulas. If you go here and you watch lecture number 1 and 2, I recorded those 2 lectures how to fix the flat slab system. So the thickness which I am remember the center to center spacing in this case, because 30 feet is the center to center spacing, so just subtract 1 column size, you got 340 inches is the clear span. Here we are using 11-inch slab thickness and it will give us 137.5 psi loading, right? Next, we have to check the slab system in beam shear, in one-way shear, and here you have to find the average thickness of the slab, right? The DL is basically is word, it is the, you see, one is DL and one is DT, right? So here this one is the DL, which is to the top of the top bar, to the center of the top bar, and one is the T, this is DT and this is I think so this is yes, this is DT and this is DL. So DL is the center of the bottom bar to the edge of the slab, right? Now take the average of these two, this will be the design effective thickness, right? And what will be the cover? The clear cover is 3/4 inch for number 4, for number 6 steel bar, and the dB, which is the diameter of the bar, which is 0.7, which is number 6 bar, right? Now this is the dead load and live load. Factor dead load will be the partition loading plus the self weight of the beam is 189 psi and the live load is 96 psi, right? The total factor load is 285 psi. Clear? So checking the one-way shear or beam shear, I already explained this in those lectures. This is because we have to check the beam shear at a distance of d distance from the face of the column. So here we have 9.51 inches, which is the average effective width, right? Effective depth. So we will consider this strip at a distance of d from the face of the column, and this is the tributary area, right? This is the tributary area. The width is 13.37 feet. How it determined? You just to subtract the half of the column size, that is 10 inch, minus plus 9.51, and you have to convert this into feet and subtract it from 15 inch. You will got this 13.37. You have to multiply this with this dimension, so you got 13.37 feet square, right? So this is the tributary area. You have to multiply this tributary area with the shear, okay, with the factor loading, and you got 3.81 kif is the beam shear, right? Now in beam shear, you already know the capacity of the concrete is 2 lambda fc prime bw into d. Lambda is 1, we are using normal concrete, and you got bw is 12 inches, right, and d is 9.51, so you got 12.09 kips, which is more than vu. So in beam shear our slab system is safe. Similarly, you have to check it in punching shear. So in punching shear, you have to consider the critical parameter, which is a distance from d/2 from all the faces of the column, d/2, right? So 4.76 inch is 9.51 divided by 2, you got 4.7. Find out the B0 distance, and after calculating the B0 distance, you have to find out this whole shaded area. This is 30 by 30. You have to subtract this critical area, which is the you see here, this is 29.51, right? 20 plus 4.76 plus 4.76, you got 29.51. This size will be same because the column is square, so you have to just multiply 29.51 with 29.51. you got the critical area you see here, and divided by 12, right? So you got you will convert this into feet. So this is our tributary area in punching shear, right, at 94 square feet. You have to multiply this with factor loading. You got 254.78 kips, And in punching shear, you already know the punching shear, the shear capacity 4 lambda for a square interior column. This table will explain this formula, and here you see 237.8, which is less than VU. So this basically shows that our thickness is inadequate, right? Is not adequate, and we have to revise the thickness of the slab to support that shear, because remember here we are not using the unbalanced moment right here. Okay, in later stages we will also use this. We will also calculate punching the shear stress due to unbalanced moment. I already uploaded lecture number 14, 15, 16, 17 on the calculation of the unbalanced moment here, right? In these videos, if you go there, you will watch lecture 14, 15, 16, 17. I have thoroughly explained those concepts, right? Now, what we have to do to go further or to design the slab system. To increase the slab thickness, this is the option. To increase column cross-sectional dimensions or cut the spacing between columns, right? However, this option is assumed to be not permissible in this example due to architectural limitations. You already know to use headed shear reinforcement. Yes, this is also the option. I have already explained headed shear reinforcement in lecture number 12 and 13, right? And I already explained this in these videos as well as right here. Okay, so the design of the headed reinforcement, the design of a bent up reinforcement, right? To use drop panels, this is the best option. We will try this option, right? This option, right? 4. Now, the drop panel should project below the slab at least 1/4 of the adjacent slab thickness. This is ACI code limitation, right? It will be projected from the slab for a distance of 1/4, right? So I already explained this in those lectures, right? Here I explained how to design a drop panel. So after that, when we are fixing the drop panel size, there are certain limitations, right? There are certain limitations which we have to fulfill, right? Now, what are those limitations? ACI code limits basically that when you are fixing the, you see here, this is the edge of this at the bottom of the slab, and here we are extending the drop panel. So this size should be such that a standard size of flyboard will accommodate this. Okay, so if you are using the nominal lumber size, this is 2x, 4x, 6x. So the actual size of the lumber is this one, and width, you see here, this is plyboard, right? We are placing that plyboard over this lumber, and you see this is the below plyboard, right? So combining all these, okay, you got the total thickness is I think so 2.25 something, somewhere around about. These are the thickness of the drop panel. You have to use these dimensions because you have to accommodate such standard lumber sizes, right? So this is very important. Okay, and similarly when you are fixing such kind of thicknesses, you have to because you remember when you are using your stepnesses K values in the case of the equivalent frame method. So when you have a drop panel system, remember you have to use tables, and those tables the tables are available for fixed sizes of the drop panel. Okay, I will explain this in when we are using the equivalent frame method, but here we are using the thicknesses. You see the drop panel thickness is 4.25 inches, but the tables which are available for the calculation of stepnesses is for 2.5 inch, for 5 inch and 7.5 inch roundabout. So you have to use such thicknesses of a flat slab system which will accommodate which can accommodate basically those tables. Let me show you those tables. And this is the PCA notes. From here we will use to calculate the stiffnesses, and here we have a two-way slab system, and here we have appendixes, right? So these are the appendixes, right? These are, and here you will see the drop panels. So in case of drop panels, you have to use these tables for drop panels, and here you see the drop thicknesses is 0.50 inches. Okay, here you see the thicknesses of a drop panel is in this case 0.25 inch. So H is the thickness of the slab, which is which is 11 inch, I think so in this case. So you have to multiply that thickness with this one. So the value which you got for a drop panel, adopt those values, but you have to cross check this value with your this limitations. So this is very important in the design of the drop panel, right? I do not explain this kind of limitations in those lectures. That's why I'm explaining those these kind of limitations while you are fixing the size of the drop panel, right? Now this is the extension of a drop panel to the one side of the drop panel from the center of the column. So 5 feet will be the one side size of the drop panel, right? L1 in one direction and L2 in other direction, right? So the final sizes you see here, this is my L1 direction and this is my L2 direction. So in L2 direction this size will be 5 feet, and in this size from the center to this will also be 5 feet. So overall slab thickness in the case of the exterior column or edge column, this is 10 feet, and from the edge of the slab it is 5.83, but from the center of the column it is 5 feet, right? Similarly in the interior column it is 10 by 10, while in the corner column you see this is 5.83 in all sides, right? So this is the final size. Now the thickness is, the overall thickness of the slab is 14.25 inch, and the thickness of the slab is 10 inch, right? And you see here the drop panel is extended from the face of the column is 50 feet, but from this from the edge of the slab it is 70 feet for the edge column or for the corner column, remember. So you must keep remember these dimensions, right? Next, for flat slab with drop panels, what we have for a slab with changes in thickness and subjected to bending in two directions, check shear at multiple sections as defined by the ACI code. These are the, remember, as in the case of the flat less slab, drop less slab, you have to just only check one section at a distance of d or at a distance of d by 2. But when you are using your drop panels, okay, you have to consider two sections basically. Okay, you have to consider two sections. One section at a distance, one section which is lie within the drop panel, while the other section will be outside the drop panel, right? So we have to check the beam shear, the unbalanced, the shear stress caused by the unbalanced movement, and the punching shear at various locations, right? At various locations. So you must check it. Now slab minimum thickness deflection, right? So here basically you see they are using again the slab thickness calculations, right? In lieu of detailed calculation for deflections, a code gives minimum slab thickness for two-way construction without interior beams. Table this, we already calculated this. This is 10.30 inches, and but not less than 4 inch. This is the limitation, right? And then this one is 9.44 inch. So here we are trying to use 10 inch, right? Now with drop panel, remember, with drop panel we are using 10 inch. In the first case which we are calculating, the slab thicknesses is without drop panels, but with drop panels we again recalculate the thickness of the slab, and here we are using 10 inch. the slab thickness as you see here, this one. How we will determine this? So this 10 inch is basically fixed over here. Now the weight of the slab without drop panel, so this is the weight. With drop panel, this one 178 psf, because in the region of the drop panel the thickness is 14.25 inch, but outside the drop panel the thickness is 10 inch. So next again we are recalculate one-way shear, but at two locations. Remember, again we calculate our D, DL, DT and D average in the same manner, right? And the covers, the dia bar is same. Again we calculate the dead weight, the live load and the total factor load. Remember, our total factor load is the 333.6 psf. You must remember this value. Check the adequacy of slab thickness for beam action one-way shear from the edge of the interior column. Consider a 12-inch wide strip, right? The critical section for one-way shear is located at a distance D from the edge of the column. See figure 7. Tributary area, I already explained this, how to calculate tributary area. And again you have to multiply tributary area with loading and compare that one with the shear strength of the concrete, and here we are safe again, right? Slab thickness of 14.25 inch is adequate for one-way shear in the case of that case, right? So this is the section you see here for beam section. It is a distance of from the face of the column at a distance of D, right? 12.75 inches. Okay, we already, this is the average value of depth, effective depth, this one, right? Now you have to just find out this shaded area, multiply with VU, you got the, multiply with QU, you got the shear, beam shear value, right? Similarly, you see here this section, this dotted line you see, this section lies within the capital drop panel, sorry, but here you see the section lies at the face of the drop panel within the slab, right? So here the thickness is different, right? And here the thickness is different, right? So this is very important. Here you see for critical section at the edge of the drop panel, slab section without drop panel, evaluate the average effective depth. Here remember, within the drop panel the average effective depth is different, but outside the drop panel the effective depth is different. Okay, so that's why they are recalculating the average depth is 8.51 inch. So outside the drop panel the effective depth is 8.51 inch, but inside the drop panel the average depth is 12.75 inches. So again we recalculate the beam shear by using the effective depth now 8.5 inch, because we have to use multiple sections as defined by the ACI code. So we have to check the beam shear within the drop panel and outside or at the edge of the drop panel, right? We are using two sections. This is very important. So with at the edge of the drop panel or outside the drop panel, the total loading is 270 psf, while within the drop panel, because the thickness is more, the loading will be more, that is 333.4 psf, right? So here the loading is decreased. Now see, again recalculate the tributary area for one-way shear, right, and multiply that with the 270. So you got 2.70. The capacity of the section will remain same. Sorry, will not be remain same because the D will be changed. Now you see 8.51, while in the first one we used 12.75. Here you see the depth is decreased, the shear capacity will also be decreased, but although we are on the safe side. Now you see slab thickness of 10 inch is adequate for one-way shear for the second critical section as well. Again we have to check this with for punching shear. So we have to consider, basically we will using the same effective loading, the same effective depth and loading. So we have to find out, here you see we have to consider one section which lies within the drop panel at a distance of d/2 from the face of the column, and the other section, remember this one is the drop panel, and this dotted line you see here, this one offside 32.75 inches. This is the critical section, right? This is the perimeter of the critical section. So that's why basically, and 6.38 inches is d/2. This is 12.75 divided by 2. You got 6.38. But here you see this, the inner dotted lines basically shows the edge of the drop panel, while the outer dotted line is the critical section, right? So here the section lies within the drop panel, here the section lies outside the drop panel. So we have to check the punching shear in both cases. The tributary area is fixed. This is the tributary area for interior column for self-weight of additional slab thickness due to the presence of the drop panel, right? So this section is basically lies within the drop panel. Assuming 5-story building, yes, this is very important. This is very important, right? Here is the tributary area, 892.6 square feet. This is tributary area. So you have to multiply this with the VQU. You got 297.9 kips, and this is the punching shear strength from this formula, and VC4 lambda FC prime B naught into D. We will got the what here, remember, yes, this is the tributary area, right? So multiply that tributary area. Remember, this is the total tributary area minus the critical area, right? The critical area you got, this is the net tributary area, and multiply this with QU. Remember, this is 334 is the loading within the drop panel, right? 297.9 kips is the loading. Now next, check the adequacy of the column dimension for axial load, right? Tributary area for interior column for live load, this one, and tributary area for interior column for self-weight due to the presence of the drop panel. Now you see 10 by 10 feet, that is the 100 square feet. We are checking here that, let's say we have, because if we have 5-story building, right, we are assuming that, let's say we have 5-story building. So all the 5-story building loading is transferred to the lower portion. So because this is step by step, loading is transferred from the first story to the lower story. Similarly, the both story will transfer their load to the third story, and similarly so on, right? So let's say we are assuming that this building is consist of 5-story. So that's why they are using 5. Already we determined QU, that is 270. Remember, 270. And tributary area is 900 square feet. Plus this is the loading 0.063, this is the loading of the drop panel. How we determine? 1.2 times 150 times 4.25, this is the thickness of the drop panel, divided by 12. We will multiply that with the size of the drop panel. 10 by 10 feet is the size of the drop panel. So we got the total axial load is 1247 kips in the case of the 5-story building. Assume 20-inch square column with 4 number 14 vertical bars with design axial strength of, this is the design axial strength. We already know how to calculate the axial capacity of a column, and we got basically 1318 kips, which is greater than PU, right? So the column size 20 by 20 inches is adequate, right? So this is the way how to check the punching shear capacity in the case of the but remember, here you have to check by your own, that you have to calculate your punching shear capacity at a distance of d/2 from the face of the column within the column drop panel, and similarly you have to consider this section at a distance of d/2 from the edge of the drop panel and recalculate B0 and find out the VC. So it will pass the shear capacity check, right? then you have to check. We do this calculation for our column size, right? Whether our column size is okay or not. So to check the column dimensions, right? Here I'm not using those calculations. You have to do by yourself, right? Here I am checking the column dimensions. So how to check the column dimensions? You have to find out your total tributary area, then the tributary area drop panel, then multiply the load this area with the loading of the slab, and this one with the loading of the drop panel, right? And multiply it by 5. If you have a 10-story building, then multiply by 10. Now you have to check, as we are using, remember we are assuming that we are using here in the column which we are using basically 4 number 14 bars. You can use 6 number 14 bar, 6 number 8 bar, 6 number 9 bar if let's say the capacity is less than this value. So you have to because the column size is already fixed, that is 20 by 20 inches, already it is you have bound by architecture, right? So you have to vary your steel value, right? So if you are increasing your value, your column capacity will be increases. So this is one a method basically how to fix the size of your column, right? This is very, I think so, it is a very fruitful information for you people, that how to fix. For example, if architecture bound you to use this column size which is fixed already by them, so how to and you see this kind of loading is coming from the top to your column. So how to find the solution for in such cases, right? Next, the size is fixed, the column size is fixed, the slab thickness is final. Next we have to run the flexure analysis and design, right? Here we are using again the equivalent frame method, and you know already that we have thoroughly discussed this equivalent frame method from lecture number 1 to lecture number 10. We have do couple of examples over it. What are those limitations? Remember, here we can use if the limitations of the direct design method is fulfilled. So you can use the direct design method, because the direct design method is more simple as compared to equivalent frame method. But if the limitations are not fulfilled, remember you will use the equivalent frame method, right? This is very important. What we have to do here in equivalent frame method, the limitations is fulfilled by the direct design method. Remember, the limitations of the direct design method is fulfilled right here, but we are using the equivalent frame method, right? So to you people will understand again, because I already covered 3 to 4 examples over equivalent frame method. This is another addition and extra example which I am covering here. Now, equivalent frame method, you already know. We did basically examples over a flat slab system and beam slab system, but we are not discussing the drop panels. Remember, when you are let's say in my those lectures, if you see, I have used basically the table 17 and table I think so table 17, right? And let me show you that table, that is table this one. In this table F14, yes, F14, we already calculate the flex and movement, right, the stiffnesses, and here you see, because we don't have without drop panels, right? So you will use this this table when you have no drop panels. But when you have drop panels, remember, then those table will not be used, and you have to use appendix 20A of PCA, Portland Cement Association notes. So I already shared that notes. These are the PCA notes. This is appendix 20A, and here you see, remember, here you people will learn that, remember, these are the tables which we are going to be used, because our size, the drop panel size is 4.25 inch. So if you multiply 0.25 with the h, which is 10 inch. So you got 2.5 inch. So this table will be used for 2.5 inch drop panel. And similarly, if you multiply 0.750 with h, that is 10, I think so you will got 5 inch. I think so 5 multiplied by 0.5 multiplied by 10, so you got 25. No, this is wrong. 0.5 times 10, you got 5 inch. So this kind of calculations will make your procedure a little bit tricky, because our thickness of the drop pen is 4.25 inch. This is the main goal in the initial of the lecture. I already explained that you have to fix the size of your drop panel such that which will fulfill this condition. Remember, you have to fix the size of the drop panel, let's say 5 inch, 2.5 inch or 7 inch, right? So because here we have to interpolate the values in between 2.5 inch and 5 inch, because the size is 4.25 inch. So this is a little bit tricky calculations. It will lengthen your calculations. So how to do this? Okay, here are the calculations. I already shared this by interpolations, some part. The rest of the thing you have to do by yourself. What we need KSB. You already know KSB. Now you have to find CN1 divided by L1. N means near end, F means far end, right? So if you have beam, this is my near end and this is my far end, right? So CN1, C means the direction of your column in L1 direction. So this is my 20, because we are using 20 by 20 inch column. So 20 divided by L1 length is already determined, that is 340, I think so, inches, right? And CN2L, this is the column size, which is CN2, right? So in this case is 20 inches. If it is a rectangular column, then it may be 18 inches, it may be 24 inches, whatever the value will be, but both these values are same. Now you have to go to that table and find out the value of your stiffness, right? So how to do this, right? First of all, you have to find out these values from your table 0.25 times of h, right? So here are the calculations. Remember, this is this table. Here you see CN1 divided by L1 and CN2 divided by L2. Here you have to search the values. My value is basically 0.00 and 0.10, because my value is 0.05. So my value lies within this value, right? And similarly in this value, right? So, and remember, CF1 is also equals to CN1, because the coefficients, well, both coefficients are same, right? This one, right? Not this one. These both values are same, right? So that's why basically CF1 equals to CN1, right? The far end size of the column, because the column size which is right here is, this is the far end. So here is CF1, this is CF1. So this size is also 20, and this size, this is CN1, right? So this is 20, this is 20, so that's why CF1 equals to CN1, right? So that's why we are using these conditions, right? These conditions. And similarly, CF2 is also equals to CN2. This is also the limitation. Remember, this is also, this one is CN2, right? And this one is CF2, right? This is CF2. So both CF2 and CN2 is same, CN1 is CF1 is same, so that's why we are using that table. Now we have to search out this value, and then we need to find out the K value, and then we have to interpolate. Okay, so how to do the interpolation I already show you. Okay, this is TA by T. This, ignore this value and also ignore this value. This is my C1 divided by L1, right? And this is my C2 divided by L2, right? Now here we have 0 and 0.1, right? So my value is 0.056, which lies between these two. Similarly here 0 and 0.1, which is 0.05, lies between these two values. Now I have to choose the value 4.79, right, which is in accordance with the 0 and 0, right? So here we have, this is 0 and 0, right? So this KNF, this value 4.75, right? And then this value 0.10 against 0.99, right? So here we have 4.79 and then 0.1 versus 0, right? 0.1, this one, and 0. So again this is 4.79. Again here we have this one 0.1 versus 0, right? So this one is 4.79, we already know it. Again 0.1 versus 0.1, right? This value is 4.9. I already explained this, right? 0.1 versus 0.1, so the value is 4.99, right? Now interpolate this value in between these two values, right? And this value in between these two values, and then this value is interpolated between this one and this one, right? Using this value and using this value. Similarly this one and this one and this one. Okay, I already explained the whole calculation of interpolation in lecture number 5, 6, I think so. So you go there and find out how I basically create this Excel sheet and how to use manually you have to calculate this value. So 4.8527 is the value of K in the case of the first, and in the case of the second my value is 5.90. Now I have to interpolate the value for 4.25 because the thickness of the drop panel is 4.25. That is the difficulty which I already explained in the initial of the lecture, that you have to fix the drop panel size such that which is coincide with this value or either this value. Again because you have to then use two tables, and from those two tables you have to interpolate the required value. So here you see this is my required value 5.58 or 5.59, right? So this is the value which you see here, this one 5.59, right? And then you will calculate case B. Case B is word, this value times ECS, modulus velocity of concrete, times modulus velocity of slab modulus velocity, that is 30 times 10 cube, right? This value, this is the 30, right? This is the width and this is the thickness, 10 cube. This is the thickness of the slab divided by 360, which is the clear span, center to center span of the center to center span, right? So you will find this value. Similarly, this is the moment of inertia IS, we already calculated it in inches. This is this value, and this value is the moment of inertia of the slab, right? This is the value, right? This 10 cube is not the thickness, okay? This is not the thickness, and this is the modulus of elasticity of concrete, right? This one you see here, this one. This is the modulus of elasticity of concrete. This is the moment of inertia, and L1 is already determined. So this is the case B, right? And what is the carryover factor? So you have to again use the same calculations for carryover factor, and you will find the value of your carryover factor. Okay, again, if you have this Excel sheet, you can do the same calculation for this value, carry over factor, which is this one, right? So you have to interpolate the value from here. Similarly, the next is find out your carryover factor value, and similarly you have to use your fixed end moment, okay, uniform load fixed end moment coefficient. This is MNF1. I will already show you this in later, that how we will calculate this value and how we will calculate this value. Remember here, fixed end moment coefficient for BA and fixed end moment coefficient for BA at a distance of 0.8 and 0, right? So I will explain this in later, right? So this is the procedure how to find out your required value of stiffness and carry over factor. Then you have to find out your KC. You already know, I explained this, what is KC in lecture number 7, 8, I think so. Again, you have to find out your TA value. What is TA value? TA divided by TB value. And what is H? Is this the height of the slab, or the clad height. This is 13 feet. This is the center to center span thickness height, and this one is H divided by HC, and thus KAB and CAB we have to interpolate. So this is the calculation. Remember TA by TB and H, and this is the H divided by HC, right? Again, remember, again you have to interpolate the values from 0.25 inch and 0.5 inch. This is very important, right? This is very important. This is the final step which I show you here, right? This value 5.32. okay, I am showing you, but this is from 0.25 inch H and 0.5 times of H. This is the combined result. Okay, so you have to repeat the same calculation the same manner. I already explained it. And what is T and TB? I already explained this in lecture number 7-6. So you go there and watch those lectures. KC. Now this is the formula for KC for bottom column. This is value is already determined, and ECS modulus of concrete to IC modulus of column with LC modulus, and this is the clears height or length of the height of the column, right? So you see here IC is a C4, which is we have a square column. So this is the moment of inertia of column. This is the moment modulus of rigidity of your concrete, and LC is the clear height. This is 156 inches. So you just plug all the values in this formula, you will get your required answer. This is for bottom column and this is for above or top column. Okay, just for bottom column only your T and TB values will be changed, right? So here you see your TB by TA value is 0.54. this value is this one, and you have to interpolate the values. You got this value, and similarly for carryover factor, this value by interpolation. So how to interpolate? So please go and watch lecture number 6-7, and for this you have to repeat the calculation as I already explained, right, in above steps. Then again for top column you have to find out your KC. KC is this value, right? And then you have to find out your KT. So KT is this value. You must know what is C. This is the torsion constant. I already thoroughly explained this in lecture number 1, 2, right? And there are multiple examples over C value, how to calculate your C value. But in this case, remember your C value will be, remember this value. This is, remember, because here this one is the effective cross section. In the case of flat slab system, it is simple to calculate C value, but in the case of columns as beams, it is difficult. This is the formula for C, which is a torsion constant, and you see X divided by Y, and you already see this is X is the total depth, right? This value, this is X and this is y value, right? And C2 is 20 inches, L2 is this one, and now you have to find your equivalent stiffness. This is KEC. So summation of KC, I already explained this in, I think so, in lecture number 7 and 8. So go there and watch those videos, right? So equivalent stiffness, after calculating your equivalent stiffness, you have to calculate your distribution factors. How to calculate it? Go and watch lecture number 8, 9, I think so. You will find how to find out your distribution factors for your column, for your beams. After that, method of analysis. Here you are free to use direct design method, equivalent frame method, moment coefficient method, whatever you want, you can calculate, right? The limitations: determine negative and positive moments for the slab beams using the moment distribution method. Since the unfactored live load doesn't exceed 3/4 of the unfactored dead load, design moments are assumed to occur at all critical sections with full factor live on all. Remember, this is the limitations for pattern loading. I already explained thoroughly in lecture number 8, 9, I think so, when you have to use pattern loading. What are the limitations? After that, you have to use pattern loading. So go there and watch it. This is the calculation which I already explained to you people, that I will show you that how to find the coefficient to calculate the fixed end moment. You already must know when we are using the fixed end moment in your undergrad, I think so, you must learn that we will use 112, right? WL L square, I think.